Good afternoon, everyone, and welcome to this week's TTC Thermal Transport Cafe seminar. Today, we have the pleasure of Dr. Geoff Wehmeyer. He's an assistant professor in mechanical engineering at Rice University. He received his bachelor in mechanical engineering from the University of Texas at Austin in 2013, and his Ph.D. in mechanical engineering from the University of California, Berkeley in 2018 before joining the faculty at Rice. His research interests include thermal property measurements of nanomaterials and switchable nonlinear thermal devices for advanced thermal management. He is the current vice chair of the ASME Heat Transfer Division K9 Committee on Nanoscale Thermal Transport. He is the recipient of Rice Engineering Research plus Teaching Award for Tenure-Track faculty at Rice, Sophia, Meyer, Farb prizes for teaching. His group research has been recognized with the NSF CAREER Award and a NASA Early Career Faculty Award. So, Geoff, floor is yours, and thank you for your presentation beforehand.
Great. Yeah, thank you, Ali. Thanks, everyone, for joining. Good morning, good afternoon, and good evening. Really pleased to be here, and thanks to Matthew and Matteo and everybody for coordinating this. It's been a great set of TTC talks, as always, and hopefully this will send us off into the summer on a good feeling. So today I'm going to be sharing our work that's looking at kind of device centimeter scale research that uses passive magnetic actuation to achieve interesting thermal functionalities like thermal switching, thermal amplification, and thermal rectification. So I'll kind of start off by, so I'll introduce my group here at Rice University in Houston, Texas. So my nanoscale heat transfer lab works both on device scale research to demonstrate switchable and nonlinear devices. We're also interested in pushing the bounds on spatial resolution for thermal experiments inside electron microscopes. And we deploy measurements and modeling to try to get a better understanding of the thermal properties of nanomaterials. And then, of course, I'd also like to acknowledge the funding sources for our group. Today's work is funded through NASA's Early Career Faculty Award and also by a Department of Energy iBuild Fellowship that's associated with Lorenzo Castelli, who's a fourth-year Ph.D. student in my group, who's led much of the work that I'll show you today. So I have 8 or 9 slides here that are kind of introducing the basic idea of what are we talking about when we're talking about switchable and nonlinear thermal devices. So for switchable and nonlinear thermal devices, these are devices which display a steady state performance that is distinct from that of a normal thermally resistive element. So when we're looking at two-terminal thermal devices, there's a variety of options that are available to folks. When I was working with Chris Dames at UC Berkeley in 2017, we wrote a review article that summarized a number of the mechanisms and potential applications of these switchable and nonlinear devices. One such device would be a thermal diode, which is a device that can rectify heat flow. If we plot the thermal transfer function of the thermal diode, the steady state heat flow as a function of the steady state thermal bias, the thermal diode exhibits a larger forward mode heat transfer at positive thermal bias, but then if you flip the temperatures to invert the thermal bias, you would get a different magnitude of the heat flow. So it's this asymmetry of the transfer function that defines the thermal diode's performance. And there are many, many mechanisms that exhibit thermal rectification behaviors. In all cases, every mechanism has to have a thermal asymmetry, which tells you whether you're forward or reverse biased. And you need to have a thermal nonlinearity such that the Q is not linearly proportional to the temperature difference across the device. You can also exhibit thermal switching, which comes in 2 flavors. We refer to the thermal regulator as a passive thermal switch. So the thermal regulator would be a device in which the steady state heat flow between T1 and T2, it depends very strongly on the magnitude of one or both of the temperatures. So for example, if the temperature T1 is the sort of set or controlled temperature for the device, then the Q versus delta T would exhibit perhaps a very large thermal conductance when the temperature T1 is high, but a very low thermal conductance when the temperature T1 is low. So here the thermal transfer function is intrinsically temperature dependent in a way that differentiates the thermal regulator or the passive thermal switch from that of a normal thermally resistive element. And lastly, you could also have an active thermal switch in which you can control the steady state heat flow between terminals 1 and 2 by applying some kind of external stimulus, maybe consuming power by an electric field, a magnetic field, some kind of mechanical pressure field, or so on and so forth. So by opening or closing the thermal switch, you can again control the heat flow through the device. So the review article summarizes many of the different possible mechanisms that have been explored, both at the intrinsic materials level and also at the device level to achieve these functions. But why would we want to have these functionalities in the first place? What can we do with these switchable and nonlinear thermal devices? Basically, we can categorize the applications into two flavors. The first flavor is a thermal regulation flavor. This is a busy plot, but I want to focus your attention on the middle representation. This is a regime map where I would plot the temperature of some engineering component that I care about, T1, as a function of the surrounding temperature, T2. In the thermal regulation application, we would like to maintain the engineering component right in its sweet spot or comfort zone indicated in blue. Not too hot, but also not too cold. So what you would like to have for a thermal regulation application is to have some kind of switchable thermal element that can cool the component down if it's too hot above the comfort zone and the surroundings are cold. It could perhaps heat the element up if the surroundings are warm and the component is too cold, but it also is able to block heat flows at other times. For example, if the component is too hot and the surroundings are even hotter, we want to decouple those temperatures in order to prevent additional heat flow. So this kind of switching between off state and on state behaviors as a function of temperature is essential for a wide variety of engineering applications where you'd like to keep some kind of component right in that sweet spot. So for example, many of the work that's been done has looked at the scenario of thermal regulation for batteries, thermal regulation for spacecraft or buildings, scenarios where you have strongly time-varying external thermal conditions, perhaps due to the day-night cycle, perhaps during charging or discharging of the batteries. Many of these devices have also been demonstrated for many decades in cryogenic systems or in thermal management of nuclear situations. They're being explored for aircraft and specific regulation applications such as atomic clocks. And then there's a growing push and understanding that this is also maybe a big deal for many electronic applications in which we would like to control precisely the temperature of the electronics over a wide range of thermal conditions. For example, if you're dealing with some kind of portable electronics. The second flavor of applications, which often emerges for these thermal devices, is to enable new energy conversion, often involving solid state devices. So in general, for energy conversion systems from sort of a thermodynamic perspective, of course, we know that in general, the energy conversion needs to take in some kind of heat flow, Q in, and then dump some kind of heat flow to the surroundings, and then it may consume power or it may produce power. So the goal of the thermal diodes, thermal switches, and so forth is to match the needs of the energy conversion device to the available thermal reservoirs in the system. Let me give you an example. If we're dealing with pyroelectric energy conversion, the pyroelectric phenomena means that as the temperature of the pyroelectric material is changing, it induces a time-varying electrical voltage. But if you have steady-state thermal reservoirs, you somehow need to couple the steady-state thermal reservoirs to the pyroelectric material to let the pyroelectric material's temperature change over time. For example, you could physically move the material in or out of contact with the different thermal reservoirs in order to induce that time periodic temperature change. Or if you have some kind of thermal diode or thermal switch, you could have an all solid state device without any moving parts that can give this kind of behavior. Similar ideas apply for other kind of caloric energy conversion applications like elastocalorics, magnetocalorics, and ideas have also been explored to improve the efficiency of thermoelectric energy conversion by coupling the thermoelectric material with the thermal diodes. So because there's such a wide range of applications that have been motivating different device developments, there's an enormous range of mechanisms and devices that have been considered over time. One way that we think about to try to categorize the different needs of the applications is by considering what kind of conductances are appropriate for different applications of the switchable and nonlinear device. So this is a regime map where I'm plotting the on-state thermal conductance on a per unit area basis, watts per meter squared per Kelvin, as a function of the off-state thermal conductance, again, per unit area. So if the device was a thermal resistor, it would have a switch ratio G on over G off of unity. But then as you have larger and larger switching, the contours would indicate going from 1 up to 10,000 here for what the thermal switch ratios are. So of course, we all agree. It would be best if we had extremely high on-state and extremely low off-state thermal conductance. So we'd like to move up into the top left of the plot here. Some applications can accommodate moderate on-state conductance as long as you have excellent insulation in the off-state, while other applications require excellent conduction for heat sinking and can live with moderate insulative capability. So when we survey the literature and look at the different devices that have been demonstrated that have been particularly targeting specific applications, we see that the demonstrated thermal switches are all over the map in terms of their on-state and off-state conductance. Generally, when we're looking at thermal management of electronics or batteries, those are operating more in the case where you really need that very large on-state conductance to prevent overheating, and you can live with just okay off-state conductance to provide the insulation, say trapping the heat inside the battery to warm it up. If we're looking at thermal applications that are looking at advanced thermal management strategies for buildings, you really need to thermally insulate the building very nicely in the off-state. So you really need the low G off, the excellent thermal insulation. And then you can accommodate or live with moderate on-state thermal conductances that when you want to let heat in or out of the building, you can do so at a reasonable level. And then the devices that have been demonstrated for nuclear power and aerospace applications come close to the ideal in terms of combining a very low off-state conductance with a very high on-state conductance. Many of these devices carry other penalties. For example, they're quite large, they're quite expensive, they're difficult to manufacture, they might have some extra research which is needed to explore the durability of the device in different situations. But because we're kind of have a lot of room to play with on this map, there are different mechanisms and different devices that are appropriate for different scenarios. Good, so the last slide I'll show you here before I kind of jump into our work that we'll talk about today is just to plug a little bit of work from a Ph.D. student, Trevor Shimakusu, who graduated from my lab last year and is now on the faculty at the University of Hawaii. And so Trevor worked with myself, and we also collaborated closely with Dan Preston, also here at Rice University, on switchable and nonlinear thermal devices that leverage liquid vapor phase change heat transfer. So Trevor's been developing jumping droplet thermal diodes using Teflon-coated aluminum surfaces to explore the durability and thermal rectification performance. And I wanted to plug this because Ali, our host, gave such a nice talk on the biphilic surface fabrication methods in a previous TTC. We also collaborated with Danny's group at University of Edinburgh to work on biphilic surface fabrication using a vinyl masking and aluminum etching technique in order to pattern complex features on aluminum surfaces to try to get improved thermal performance under phase change heat transfer conditions. So if any of these are interesting to you, I'd recommend that you reach out to Trevor or connect with him to learn more about some of his ongoing work pushing on the thermal diodes and thermal switches behaviors. But today I'm going to be focusing on our group's research that's been demonstrating thermomagnetic devices. So I have two parts of the talk. The first part, we'll talk about devices that are used for thermal switching and thermal amplification. The device that we're demonstrating and we'll talk about today is what I call a thermal transistor device. So the thermal transistor device would be a 3 thermal terminal element in which the temperature at the thermal gate, Tg, can passively switch and even amplify the heat flow from a thermal source to a thermal drain. So if we have a thermal transistor element shown here, it has 3 thermal temperatures, and then there are 3 heat flows which could be entering or exiting the device. So if we focus on the switching behavior, if we plot the heat flow going through the thermal drain, QD, as a function of the source to drain temperature difference, Ts minus Td, if the gate temperature is high, the device that we demonstrated has a high on-state thermal conductance, meaning that at low source to drain temperature differences, you can drive very large drain heat flows. But if you have a low gate temperature, it switches to a small off-state thermal conductance, meaning that even at large temperature differences, there's minimal heat. So this transfer function is what we use to evaluate the switching capabilities. We'll come back later and talk about the amplification aspect of the thermal transistor. So the concept of thermal transistors was proposed almost 2 decades ago within the context of nonlinear nanoscale heat conduction and anharmonic one-dimensional chains. There's been a number of other mechanisms that have been proposed in the past with quantum electronic systems, with thermal radiation and near-field thermal radiation. But until 2023, there was no physical embodiment, no experimental demonstration of this 3-thermal terminal device that can display the switching and the amplification. So the work that I'll talk about for our thermal transistor and for all of the devices that I'll show you today rely on passive thermomagnetic actuation. So the sort of secret sauce for these devices is the soft magnetic material gadolinium, GD. So gadolinium is a soft ferromagnet that has a very convenient Curie temperature near 300 Kelvin. It's commercially available in millimeter and sub-millimeter thick foil formats. So if you put this device in the PPMS and you measure the magnetic properties as a function of temperature, you see the expected behavior where in the high temperature paramagnetic state, there's a very weak remnant magnetization of the gadolinium material. But then as you cool it below its Curie temperature, close to 20 degrees C or so, you exhibit a larger enhanced magnetic response at lower temperatures as it's in its ferromagnetic state. And similarly, if you plot the magnetization as a function of the magnetic field, we can see that as you decrease the sample temperature from 300 Kelvin to 270 Kelvin, you get a dramatically enhanced magnetic response at lower temperatures when it's in the ferromagnetic state. And gadolinium is a soft magnet, meaning that as you reduce the external magnetic field, there's a very small remnant magnetization. So the concept of all of the devices that I'll show you today is that if you put this soft gadolinium material near some kind of boring permanent magnet, which here we use these neodymium iron boride magnets. Basically, you just think of it like a fridge magnet at your house with a north and a south. When the gadolinium is cold, there's a strong attractive force between the gadolinium and the neodymium magnet. When you heat the gadolinium up, the gadolinium transitions to its paramagnetic phase, and there's a very weak magnetic interaction. The gadolinium would just fall off if you have some kind of force that would remove it from the neodymium. And then the process is entirely reversible. If you heat the gadolinium up, it's a paramagnet, no magnetic interaction. If you cool the gadolinium down, it's a ferromagnet, strong attraction. So you can cycle it back and forth as many times as you like because it's just a phase transition between the paramagnetic and the ferromagnet. So here's how we leverage this temperature-dependent magnetic interaction to create a thermal transistor element. So I'll show here first what the device looks like in the low gate temperature off state. So we have a thermal source and a thermal drain, which are simply connected to thermally conducting copper elements with a thermally insulating spacer. And then we have a mobile shuttle. The shuttle has a neodymium magnet on the shuttle. The shuttle can translate back and forth. In the low temperature off state, the shuttle is contacting the thermal gate, which has a gadolinium foil pasted onto the gate. So in the low temperature off state, the gadolinium is ferromagnetic, and it has an attractive force to the neodymium magnet on the shuttle, which can pull the neodymium into contact with the gadolinium, opening a gap between thermal source and thermal drain, as visualized in the optical image. But when you heat up the temperature of the gate above the Curie temperature of the gadolinium, then the gadolinium no longer is magnetically participating in the problem, and the neodymium magnets that are on the shuttle are attracted to these smaller neodymium magnets embedded within the thermal source and the thermal drain. So now the shuttle is actuated into steady state contact, bridging the thermal source and thermal drain and enabling heat flow through the device. So in the low temperature off state, your gap is open. You only have essentially parasitic heat flow. Then in the high gate temperature on state, you're in contact and you have that strong conduction heat flow. The magnitude of the heat flow turns out to be limited by the thermal contact resistance at the shuttle source drain interfaces. So it's sensitive to the presence or absence of vacuum. It's sensitive to the presence or absence of thermal interface materials at this interface. So if the video plays here, this is showing the transition of the device. So if I begin with the device in its off state and I begin to heat up the gate, you can see the transition occurs from the off to the on state. If I have initialized the gate to be warm and I begin to cool the gate down, then as the gate eventually decreases its temperature, then you get that magnetic actuation to break the gap. This is a steady state system, meaning that as long as you hold the gate, source, and drain at certain temperatures, the position of the shuttle does not change with time. What I'm indicating here is simply the switching or the transition between these two. So in order to quantify the thermal switching ratios of this thermal transistor device, we use a classic ASTM reference bar method in high vacuum conditions. So we mount the thermal transistor between a heated upper bar and a cooled lower bar. And then we also have a separate mount where we place the gadolinium foil in the gate temperature. So the raw data that we get from these experiments is as follows. We maintain a certain top side hot temperature and bottom side cold temperature. And then as a function of time, we modulate the gate temperature. So if we start off with the gate temperature cold, then the device is in its off state. There's very little heat flow across the device. So the thermocouples on the upper bar are all clustered together and the thermocouples at the lower bar are all clustered together. But then when we increase the gate temperature to initialize the thermal switching, there's a much larger source to drain heat flow, which drives large temperature differences within each of the reference bars. And again, this is entirely cyclable and repeatable. So we can do the measurement several times to measure the on and off state thermal conductances once you've reached the quasi-steady state phase. So here's our measurements of the thermal transfer function of this first thermal transistor demonstration. So when we measure the drain heat flow in the on state in red and in the off state in blue, we can see that there's a gate-driven source to drain thermal switching ratio around 100 or so. There's large error bars because it's actually very difficult to measure the very low off-state heat flows in the device. But we can see that there is very substantial thermal switching that's associated with the physical making and breaking of contact between the thermal source and the thermal gate drain due to the gate temperature. So this first demonstration of thermal switching was a key component towards demonstrating the thermal transistor action. We also wanted to explore the hysteresis that was associated with the device. How much more do you have to heat it up to have it transition from off to on? Then you have to cool it down to have it transition off at the low temperature state. So we can do measurements where we keep the source to drain temperature difference fixed and we measure the drain heat flow as a function of the gate temperature. So if we initialize in the off state of the cold gate temperature, heat it up, once you get to 27 degrees C or so, you transition to an on state. Then if you cool it down, it eventually switches off at around 20 degrees C or so. So we get this kind of hysteresis window in the range of 5 to 10 degrees Celsius for different gap sizes and different device configurations. This thermal deadband is important in different thermal applications because it determines basically the external temperature ranges under which the device could effectively switch between the on and off state. And then we also tested and demonstrated the thermal actuation over more than 1,000 cycles to show that the behavior would be repeatable over at least lab scale experimentation. The last thing that we wanted to show for the thermal transistor was this demonstration of heat flow amplification. So now this word, so heat flow amplification, what are we talking about amplification? You know, we're trying not to violate any of the laws of thermodynamics. What do we mean about, you know, amplifying heat flows? Well, in this case, the demonstration of heat flow amplification in the definition is similar to that of electrical amplification in an electrical transistor. A heat flow amplifier in a thermal transistor would be a device in which a very small amount of heat flow into the thermal gate can drive a much larger change in the source to drain heat flows. So in order for us to demonstrate this heat flow amplification, we mount a heater on the gate material, record how much energy is consumed by the heater to control the temperature of the gate, and then combine that with finite element modeling to assess how much heat flow is flowing from the gate into the thermal transistor. So from these measurements, we can then extract the thermal amplification beta parameter, which is the change in the drain heat flow induced by a change in the gate. So we're going to plot this amplification parameter as a function of how much heat flow is flowing into the gate. So if we're in the situation where nothing interesting is happening, we're having mild amounts of heat flow that are coming into the gate, but the heat flows are not large enough to increase the gate temperature and induce the switching, then as expected, the beta parameter is small. Any kind of linear thermal system has a beta parameter which is less than 1, indicating that there is no switching and there is no amplification. But once the gate heat flow increase is larger than the threshold amount required to increase the temperature above the ferromagnetic to paramagnetic transition of the gadolinium, then even a small amount of gate heat flow can drive a very large heat flow from the thermal source to the thermal drain. This source to drain heat flow is dependent on the source to drain temperature difference. It scales linearly with the source to drain temperature difference. So we can see that if you have a large source to drain temperature difference, you can get these thermal amplification ratios that are large as 30, as long as you've been able to induce the switching. So to summarize, this was the first experimental demonstration that showed the thermal amplification phenomena in the 3-terminal resistor, meaning that the small change in the gate heat flow drives a large change in the source to drain heat flow, as long as you can successfully cross over that off to on transition. And since the time where this paper was published, there's been several other demonstrations using thermal radiation or even using some thermal expansion effects, where folks have demonstrated the thermal transistor action can indeed occur, and you can get this kind of heat flow amplification using a variety of mechanisms. The last thing that I'd like to talk about in this thermal switching section before I move on is a similar two-thermal terminal concept for a passive thermal switch or a thermal regulator. This paper was published several years ago. This two-thermal terminal concept is a more conventional device of a thermal switch, but it leverages the same essential operational mechanism as the thermal transistor. We again have a gadolinium material which is interacting magnetically with some neodymium magnets that are on a mobile shuttle and a neodymium magnet that's placed in a stationary top plate. So when the gadolinium temperature is cold enough that the gadolinium is ferromagnetic, then the shuttle is pulled out of contact and opens a gap. This gap blocks the heat flow from the bottom of the device to the top of the device, meaning that the thermal regulator is in its off state. When you heat the gadolinium up, it transitions to its paramagnetic mode. It's no longer magnetically interacting. The neodymium magnets in the shuttle attract the neodymium magnets on the top plate, and so the device snaps into contact. Now there's a pathway for heat flow from the bottom of the device through the top of the device. So we performed measurements of the thermal switch ratio and found thermal switch ratios for this device around 30 in vacuum. It's only around 2 or so in air because of the parasitic heat conduction through the air. You can get 5 degrees C thermal hysteresis and cycle it over thousands of cycles. And this demonstration is potentially exciting for future spacecraft thermal management applications. The switch ratios of the magnetic device are not as good as the switch ratios of the highest performing aerospace thermal switches that rely on melting of waxes or differential thermal expansion of metals. But the device is much more compact and tends to have a lower thermal hysteresis, which might be advantageous in some. Good. Now I'd like to move on to the second portion of the talk, where we're again discussing thermomagnetic devices, but now I'm interested in thermomagnetic devices that can rectify heat flows in thermal diode behaviors. Our group has published 2 different but related experimental demonstrations of oscillating thermomagnetic devices. The first demonstration in the Advanced Functional Materials paper back in 2022 leverages an unstable balance between magnetic forces and gravitational forces to achieve oscillations. So what I'm showing you here in the video that's playing is a scenario where we've maintained the top of the device at a fixed temperature, 60 degrees C, and we maintain the bottom of the device at a fixed cold temperature, 10 degrees. And what we observe, even with these steady state temperature differences, is that the shuttle shown in the middle here exhibits these linear oscillations upward and downward. These oscillations are helping to transfer heat via advection across the gap, as long as the shuttle is oscillating. And then the cartoon schematic on the right shows the particular illustration of the device where we have a hot temperature, a cold temperature. There's a neodymium magnet embedded in the top surface, and the gadolinium is on the shuttle. More recently, we've also demonstrated a similar thermomagnetic device, but instead of leveraging gravitational forces in order to pull the shuttle downwards, now we have these mechanical springs which are acting to pull the shuttle out of contact with the top magnet. So again, if I have a top temperature of 60 degrees C and a bottom temperature of 10 degrees C, we see that the shuttle can exhibit these time periodic mechanical oscillations which are transferring heat from the heated top surface to the cooled bottom surface. And the illustration again shows it's similarly just a neodymium magnet, a gadolinium magnet, and springs. So I'll focus mostly on this spring-based device when I'm describing the thermal rectification behavior and the oscillation mechanism. So why does it oscillate, and why is it a thermal diode? I'll talk for a little bit about the mechanism and what differentiates these thermal diode devices from the thermally switchable devices that I mentioned. So I'll focus on the spring-based device, and I'll focus first on the reverse mode where the shuttle is not oscillating, it's just sitting there. So if the top neodymium magnet is cold, or the temperature of the bottom surface of the spring is hot, the shuttle doesn't do anything. It doesn't oscillate. If you initialize it in contact with the bottom surface, it stays on the bottom surface. If you initialize it in contact with the top surface, it's going to stay on the top surface. There's a stable interaction between the magnetic forces and the mechanical forces that lead to steady state behavior, such that heat is only transferred parasitically via conduction through the air, radiation across the gap, or conduction through the mechanicals. If I plot in this regime map format on the right, the modality of the device, the state of the device is a function of the neodymium temperature or the spring temperature. This reverse mode in yellow is again the scenario where either the neodymium is cold or the spring is hot. So there's no oscillations in this case. Where we observe the oscillations, the videos that I was showing you on the last slide, is the case where the top neodymium surface is hot and the bottom spring surface is cold. So if you're in this upper left quadrant of the regime map, you get these steady periodic oscillations that transfer energy across the device due to the motion. So why does the device oscillate? We can understand this by comparing the spring forces that are acting downward on the device to the magnetic forces that are acting upward on the device. This is a busy plot, but it's finite element calculation showing the force as a function of the spacing between the magnets. So the spacing between the magnets is different depending on where the shuttle is in upper contact with the upper surface or is in contact with the lower surface. So if I kind of walk us around this cycle, okay, and then the two curves are the two magnetic curves. F magnetic is when the gadolinium is warm, and then F magnetic in blue at 19 degrees C is when the gadolinium is cold. The black line here is the spring force that's acting to pull the shuttle out of contact. So what happens from step 1 to step 2 is that when the shuttle and the gadolinium magnet get sufficiently cold and they're sitting on the bottom surface, when the gadolinium gets cold, it's attracted to the top neodymium surface, which reduces the distance between the neodymium and the gadolinium magnets. So from step 1 to step 2, that's when the shuttle is moving upwards in the cycle. When that cold shuttle comes into contact with the heated top surface, the gadolinium temperature will increase, which decreases the magnetic attraction force. And as soon as the gadolinium gets warm enough that the attractive magnetic force can no longer counteract the mechanical force from the springs, then in step 3 to step 4, the springs will pull the shuttle out of contact with the top surface and back into contact with the cold bottom surface. Then from stages 4 to 1 of the cycle, the device will cool. The gadolinium gets colder and colder until it magnetizes and has a strong magnetic interaction with the top neodymium magnet, at which case it will come into surface with the top of the device and reinitiate the thermal cycle. So we can perform measurements where we put thermocouples at different locations in the device to assess the temperature profiles that are occurring. So these are measurements of the temperature as a function of time. If we have a certain nearly steady state hot temperature and nearly steady state cold temperature, the thermocouples that are located on the shuttle exhibit these time periodic oscillations as the shuttle is coming in or out of contact with the top and cold surfaces. And what we can see and extract from these measurements is that the shuttle temperature excursions are localized within these temperature ranges, this temperature top to bottom and temperature bottom to top transition. The temperature top to bottom and the temperature bottom to top are just the temperatures at which these transitions occur. Here, 22 C and 19 degrees C for the spring-based device. We can develop simple thermal models to try to describe and predict the shuttle frequencies. The simplest model that you can use would be a simple thermally lumped model, where you assume that the dominant resistance to heat flow is at the interfaces between the shuttle surface and the top or bottom stationary plates, but that the heat can readily conduct through the shuttle material itself. In this scenario, simple lump thermal modeling would allow you to predict the oscillation frequency as a function of the different transition temperatures, the boundary condition temperatures, T cold and T hot, and it depends on the thermal time constants that are associated with the motion of the shuttle, which we could fit to the experiment. So when we use this thermal model to show how the oscillation frequency depends on the temperature difference across the device for different cold side temperatures, we can see that there's pretty good agreement between the thermal modeling fits and the measurements of the different oscillation frequencies. So to explain the plot a little bit, if the temperature difference is too small, such that the hot temperature is not hot enough to initialize the oscillation, then the shuttle is stationary. But then once you heat the shuttle up such that the hot temperature is warm enough to initialize the oscillation mechanism, then it tends to oscillate faster as you increase the hot side temperature. We can also go ahead and use our steady state thermal conductance measurement techniques such as the reference bar, or even simpler sort of film heater-based measurements with additional thermal insulation around the device to determine the heat flow as a function of the temperature difference. So what we see to understand the thermal diode behavior of the material, we focus here on the case where the spring temperature is, say, at 15 degrees C, and then we're changing the neodymium temperature. So if you're getting that neodymium temperature up to, say, 25 degrees C or so, then we observe these oscillations that are transferring heat across the device. But if the hot side temperature is not warm enough, then the device is in its reverse mode when, for example, the neodymium is colder than the spring. So we can get these thermal rectification ratios, which depend on the temperature difference, but are on the order of 5 or 10 or so for different devices. The line that's in the comparison to the data point here is the prediction of the lump thermal modeling. The lump thermal modeling would state that the time averaged heat flow when the shuttle is oscillating is proportional to the oscillation frequency. And then the constant of proportionality, the mass of the shuttle, the heat capacity of the shuttle, and the difference between the top to bottom and bottom to top temperature. This would be the energy which is transferred by the oscillating shuttle per oscillation. And what we can see is that the same thermal time constants that we fit to with the heat flow measurements agree quite well with the predictions of the shuttle frequency, indicating the lump thermal model is reasonable in this particular experiment. As a little bit of an aside, we also wanted to understand, like, what are the ultimate limits to the thermal rectification that you can achieve with this particular mechanism? We know that the lump thermal model is going to break down if we can get better contact conductances at the interfaces between the oscillating shuttle and the stationary plates. So in order to understand the maximum heat flows that could be achieved in these situations, we had to go ahead and use the separation of variables technique to analytically solve for the temperature profiles inside the oscillating shuttle for arbitrary thermal contact conductances. So that's described in this IJHMT paper from 2023 here. The paper shows, as expected, that the lump model works well when the BO number associated with the thickness of the shuttle, the thermal conductivity of the shuttle, and the thermal contact conductance at the shuttle plate interfaces are both small compared to, or either the top or the bottom BO numbers are small compared to 1, then your lump model approach that we were using previously is a good approximation. So that's why for our copper or aluminum shuttles, we get good agreement with the lump model. If we wanted to maximize the thermal rectification ratio and we want to understand what's the most amount of heat that could be transferred due to the oscillations of the shuttle, what we see is that if the BO numbers at the interfaces are sufficiently large, then you're limited by the thermal resistance to conduction within the shuttle itself. So the upper limit on Q forward is just set by like a Ka delta T over L thermal conductance or heat flow through the device itself. So we're building and have some ongoing work to try to assess the predictions of beyond the lump model prediction. But what I want to wrap up with today on this thermal diode demonstration is looking at a motivating application that we've been exploring. Where could we go ahead and use these magnetic thermal diodes, or at least understand why they might provide an advantage compared to traditionally thermal resistive elements. So this paper that came out last year in Cell Reports Physical Science is looking at the scenario of the multi-season passive variable insulation, or PVI. So the concept of the passive variable insulation is that this is something that you can install within the walls of the building envelope that would either let heat through the building at some times, but block heat flow through the building at all times. So usually, of course, the traditional approach for insulating a building or your house is that you want to have large R values, big static thermal resistances to decouple the interior of the building temperature from the exterior or ambient temperatures. But this fails to take advantage of the fact that sometimes you can actually use the natural gradient of the temperature differences to be advantageous in a way that would allow you to cool down or heat up your house without having to pay for it or consume electricity for the HVAC. So the passive variable insulation idea is that, hey, okay, maybe during the warm summer day when it's hot outside and cold inside, you want to block the heat flow. But then during that cold summer nighttime, when it gets, like if you're in a desert environment, it gets very cold outside, you can actually intentionally pull heat out of the building, dump it out through the passive variable insulation to cool down your building without requiring the air conditioning consumption from your HVAC. Or perhaps you might want to get that passive heating on a warm winter day. So we agree during the cold winter night, you need to thermally insulate your house to trap that heat inside. But if you have a nice, warm, sunny winter day, you could actually use the heat from the exterior of the house, have it conduct through the walls of the building, and reduce the amount of energy that you need to use to heat up the house. So there's been a number of different mechanisms and devices that have been used to achieve this passive variable insulation. There's a lot of great work going on for things that you can put on the exterior of the building, things you can put on the roof of the building. The existing solutions for devices that you can install within the envelope of the building, right now they either work for the passive cooling scenario or they work for the passive heating scenario. You can't use them for both. And in fact, for those devices, if it's advantageous for the passive cooling, it can actually lead to excess heat losses or disadvantageous behavior during the alternate season. So what we proposed and demonstrated was a multi-season passive variable insulation concept that utilizes two of these thermal diodes in an anti-parallel configuration. So if I plot the regime map of the state of the circuit on or off as a function of the interior temperature T in and the outside wall temperature T out, what the thermal diode devices give you is you can get that passive cooling when the building is hot and the outside is cold. You can get the passive heating when the outside is hot and the building is cold, and then you can block the heat flow at all other times. That's the yellow state here. So try to help your building stay within that narrow comfort zone. So we constructed and tested the application of this multi-season passive variable insulation device. So if I show the thermal circuit element on the top left, we have two diodes that are in an anti-parallel configuration. Diode 1 provides the passive cooling effect. Diode 2 provides the passive heating effect. And then the optical image of the device is shown below. So we went and measured the steady state thermal conductance of the device as a function of all of the different interior and exterior temperatures for the thermal circuit shown here. And we see that we can get this expected behavior for the passive variable insulation system where diode 1 gives you the passive cooling. It's on when the interior temperature is hot and the exterior temperature is cold. Diode 2 gives you that passive heating case where the interior is cold and the exterior is warm. And then the devices remain off in the scenarios where you want them to remain. So this was the first demonstration of the multi-season passive variable insulation within the building envelope that shows you both the passive heating and the passive cooling capability. It can give you the thermal circuit switch ratios of around 3 in air, and it never overcools the system. What I mean by that is that you can never get the building too cold during the passive heating, which would be like kind of over here somewhere, or you can never get it too hot during the sort of passive heating scenario. So we think that there are aspects of this idea that are interesting and promising. Of course, if you actually want to implement this in a real building, there's tons of consideration. It needs to be dirt cheap. It needs to be highly reliable. Of course, it can't be loud. You know, if it's clicking as it's oscillating or there's motion, that would be highly distracting. So there's a number of challenges that would need to be addressed for future implementation of these devices. But we think the concept of using these thermal diodes for the multi-season passive temperature control of the buildings is pretty promising. And there can be future research to explore scale up and ultimate development or implementation. Good. So with that, I'd like to go ahead and wrap up the talk here. So today I talked about thermal switching, thermal amplification, and thermal rectification in centimeter scale devices that are actuated using the temperature-dependent magnetic properties of this gadolinium material. So depending on how you configure the different magnets in the device, you can get devices such as a 3 thermal terminal resistor that can switch or amplify the heat flow from a thermal source to a thermal drain via the temperature of the gate. Or you could get devices that exhibit steady periodic oscillations under steady state temperature profiles that can give you thermal diode-like behavior when the forward mode is exhibiting the oscillations and the reverse mode is stationary. And then we're interested in exploring different applications of these devices for advanced thermal regulation or advanced energy conversion. Good, so thank you all for joining today. I'm happy to take any questions that you might have.
Thank you, Geoff, for the nice presentation. So I guess the floor is open for any questions. Well, maybe I can start with the first question. So which material properties or interface properties is the most important and dominant that affect the system performance, in your opinion?
Yeah, thanks, Ali. So right now, the performance of the devices in the on state, like how much heat can we transfer when it's oscillating or how much heat can we transfer when it's on, is basically governed by the thermal contact conductance at the interfaces. So now, because we just have some kind of metallic surfaces that have some surface roughness associated with them, and the magnetic forces that are, or the spring forces that are pulling them into contact are not so strong. So because of that, the interfacial thermal contact conductances at those metal-metal interfaces are on the order of maybe 1,000 or so watts per meter squared Kelvin, which is not that large. So those pressed contact interfaces are currently limiting the on-state heat transfer. So the devices that we're showing here usually use a thermal interface material at that interface, maybe like that thin graphite foil or a thin copper foil. Something that it's not too sticky, so you're not going to impact the hysteresis of the device because you still have to make and break the contact. You can't permanently adhere them together. We've had less luck with like thermal pads or other kind of compressible thermal interface materials, so we've tried that. Under some situations, even some kind of fluidic, some greases have also provided higher on-state conductances and are durable under at least tens to hundreds of cycles. So if you have that kind of liquid thermal interface material, that could be appropriate in some scenarios as well. But yeah, that's what really limits the on-state. In the off-state, it's already very thermally insulating in the off-state if you're doing it in vacuum. You could reduce the off-state ratios even further, maybe with some kind of low emissivity coatings or with lower thermal conductivity mechanical supports to prevent that parasitic heat flow.
Thanks.
I guess one question about the oscillating devices. So it somehow seems initially attempting to think that this might somehow be equivalent, even if this would be kind of impractical or impossible, to like bringing surfaces in and out of contact, like at a, certain times or frequencies. But then I guess from looking at like the plot in the bottom right, we see that is not, I guess, the same, right? So fundamentally, if that's correct, can you explain kind of why that's the case? Does it come down to the mass, that the shuttle has a mass, right? Versus if you're just bringing surfaces in and out of contact, that's not the case?
Yeah, that's a great question. So like, yeah, what's the difference? Like, why does the transistor get 100x switching, but the diode gets like 5x or 10x sort of? Like, why are they similar or dissimilar? Yeah, so it's basically in the thermal transistor case, there's a steady state configuration of the different surfaces. And so you just have heat flow that, like there's a thermal resistance at each of the pressed contacts that's acting in series. For the oscillations of the thermal diode, if I kind of like go back to the kind of math here, the things that you can do to control how much heat is being transferred would be to modify the thermal time constants again at the interface to show how effectively you can transfer heat from the stationary plate into the oscillating shuttle to raise or to lower the oscillating shuttle temperature. Right now, the lump model is appropriate when the thermal contact resistances are somewhat large at the pressed surface interfaces. If we got to the limiting case where we had really big BO numbers, so really big thermal contact conductances at the interfaces, then the on-state thermal conductance that you get that's associated with the conduction resistance through the device would be exactly, I think, what you're saying. Like, so the maximum thermal conductance that you would get if you had really good contact resistances would be very similar between the oscillating device and the thermal transistor device. But because the contact is somewhat poor right now, that's why you get worse performance with the oscillating device than you would get with the thermal transistor.
Yeah, I think that's the part I was missing. Thanks.
Professor, I had a question. Most of the experiments that you showed right now were in Cartesian coordinates, where you had two stationary plates and an oscillating shuttle, which also helped you increase the highest contact area for heat transfer when it hit one of the two plates. But my question is, what is your opinion on how to do this experiment in a cylindrical coordinate system? Which means think of you have a hot rod in the center. Your objective is to control the temperature of that rod. And then you have a cold annulus or a cold annulus rod kind of thing. Okay, so you have a surrounding rod whose temperature you can control through any other active cooling mechanism. And then you have this shuttle, but now this shuttle is not going to be a Cartesian coordinate shuttle. It has to be cylindrical. But the problem here is that the area keeps on changing as you go from inner radius to the outer radius. Whereas here, the area did not change. It is a constant, right? You understand here, this is constant area, but there your area changes. So what is your opinion in performing experiments in a cylindrical coordinates for application like that?
Yeah, it's a very interesting idea. I haven't thought about it deeply. Possibly you could have some kind of device for the shuttle motion that includes like it's sort of that has rigid components and flexible components. Because I think if I understand what you're saying, the problem is that as like if you want to translate from the inner radius to the outer radius, you cannot simultaneously make good contact on the inside and on the outside. Maybe you could, depending on the radii of curvature that you're looking at, if you just had a small enough gap size between them, if the shuttle is not moving very much between the inner and the outer radius, perhaps it could be approximated. If you wanted to have a larger stroke, a larger translation, maybe you could do something where you have like two rigid components and then a flexible thermal linkage between them, such that when you actuate it outwards, the sort of flexible components would expand. Like maybe you have a thermal braid of copper or something like this, which is connecting those situations there. But yeah, I think this is you raise a very interesting point. I haven't thought very much about how you would extend these kind of concepts to situations where just kind of linear translations would not be very useful. There's definitely also rotary thermomagnetic devices that have used. So in some cases, like if it's just easier to work with some kind of rotation system rather than a linear translation system, that could also give you some further room to play with.
And the second question, which I think Matthew and Professor Puji wants to say something. Yeah.
Oh, go ahead, Vish. I can ask later.
Yeah, so this is something interesting for quantifying the heat that can be to quantify the heat through repeated oscillatory motion of the shuttle. There is a similar model in pool bowling. We have something called Mikic-Rozanov model, where he quantified the heat that is leaving a hotted surface through repeated contact of the liquid that is continuously replenishing the surface as the bubble continuously departs at a set frequency. So you do have the frequency information at which the shuttle oscillates. And although you have used a model to quantify the heat that is being leaving, but this is something to see if that model can also work, because that works on the principle of heat diffusion through repeated contact of the liquid to the heat or hot surface. You have just something to think about it. I don't know if it will work, but Matthew and Professor
it's basically the same equation, I guess. It's sort of during the bubble ebullition cycle. Yeah, instead of the, of course, you have the latent heat term instead of the specific heat term, basically. But it's a very similar problem, I guess, where as long as you know the bubble growth.
Because I know in that equation we get the thermal diffusion length. So I think you have square root of pi alpha, and so thermal diffusivity also plays an important role there. I'm pretty sure it would come somewhere in this equation, but I remember in that equation we also have the thermal diffusivity of the liquid that plays a role. But yeah, that's all. Thank you so much for your.
Thanks. Yeah, that's a very fruitful suggestion. I appreciate drawing that analogy.
Yeah, Geoffrey, I really appreciate your talk. It's really, I say, a different flavor and very refreshing for this community. I have a question because you mentioned different potential applications, and somehow one of the previous participants hinted to that. I wonder whether you have started to look specifically on how you can apply this sort of devices to some of those applications, or if that's something which you have planned for the future.
Yeah, let me maybe just pull some of these kind of list of applications back up.
Yeah.
So definitely we started working on all this magnet stuff because we had a project from NASA to develop new heat switches for the spacecraft application. So I think this is like a pretty promising avenue for high thermal switch ratio devices. And it's more flexible in terms of the cost. You know, like if it's a high performance device, if it were sufficiently compact, sufficiently light, and sufficiently durable, then even if cost were a premium, you know, if it gave you that necessary thermal performance, perhaps they could accommodate it. On the other hand, the buildings application is the other one we've looked at closely. The buildings market is much bigger. So if you want to start a company or something to push on it, of course, maybe the buildings is a nice way to go. But the insulation is like cheaper than dirt. So how are we going to compete with the thermal insulation, basically, in terms of the performance of the device? It's a challenging problem in terms of scale up and in terms of the material. Like all the magnetic materials are too expensive to use, basically. So you have to be a little bit more creative in terms of like, okay, what's your allowed design space? And then the one that I think is receiving more attention is maybe like as we're moving to the big, of course, everybody knows about all the data center cooling problems, electronic thermal management problems. Are there situations in which we can use these thermal management devices to deliver that high cooling when we need it to the electronics, but then save the energy such that we're not overcooling the devices when we don't need to overcool them? So using these thermal diodes and thermal switches to have a more targeted approach for thermal management. There's been work from this community on doing so with liquid vapor devices. There may be some conduction device-based opportunities as well to integrate in to the electronics cooling to reduce the power consumption that's used for the data center cooling. So those would be the three applications that maybe seem like potentially like future research investments in these areas could be pretty impactful.
Thank you. So regarding the comment, Vish, on the essentially pulsating system, right? So when you're the big difference for me between the say the philosophy of say the quenching model of Mickey and Rosen in your case is that you're only always relying on the same system and the same phenomenon, which is conduction. So energy doesn't go anywhere else. In the model of Mickey and Rosen for boiling, heat is being actually removed by convection. So there is a fundamental difference, and that's you have another phenomenon essentially taking the heat away at every cycle. So my feeling is that the best you can do is probably not is not the fastest you can do it, or you may not have the same benefit because your cold temperature will not essentially will not be kept low by something else, which is convection in boiling. I could have phrased this differently, but that's the idea.
Yeah, in some ways it's a little bit analogous, I think, Matteo, and like because we still there's like this big heat sink, like the whole thing's on some chiller, keeping it at some fixed temperature.
Yeah.
So heat is like being pulled out of the shuttle when it comes into contact with the cold bottom surface due to the physical motion of the shuttle in a manner that's like maybe somewhat analogous to how the physical motion of the bubble departure is removing heat flow from the surface.
Sure. Yeah. No,
so
that
there
part,
is still like heat coming in and heat coming out in the same way, even though the
that
mechanism
part,
is the same.
that part I agree. What I'm saying is that basically your limit is going to be how fast you cool at the bottom.
Yeah, yeah, exactly.
That's going to be your bottleneck.
Yeah.
Okay. Well, thank you, Geoff.
Cool. Thanks, Matteo.
Yeah, I think we don't have any more questions. I'm looking at the chat as well. Yep. So thank you, Geoff, for nice talk. And yeah, we are looking forward to the next TTC session.
Yes, thank you, Ali, and thanks everyone for joining today.